Swayam Prabha. Digital India. Educated India.
Hello and welcome to today's lecture. So, we would like to continue and discuss about two very important distributions today, but before I start I would like to briefly review what was discussed in last class. Okay. So, in last lecture we discussed about two distributions, the Poisson distribution. Okay. So, for the Poisson distribution, okay, probability of x equal to I is given by e to the power minus lambda, lambda to the power I by factorial I is equal to 0, 1, 2 and it goes up to infinity. Okay. So, Poisson distribution, the Poisson random variable is a discrete random variable, okay, but it can go up till very high values. Okay. And what we had demonstrated in last class was for the Poisson distribution, your expectation and variance both return you a value of lambda. Okay. And so, Poisson distribution also one more thing. So, for large n and small p, so by small I mean let us say p is order 0.1. So, we can have the binomial random variable is almost equivalent to the Poisson random variable with parameter lambda is equal to n times. Okay. So, other than the Poisson distribution, the other distribution which we discussed yesterday was the uniform distribution. Okay. And for a uniform distribution, okay, in a range alpha to beta, your probability is uniform. Okay, it is a constant. And this constant, so this c is nothing but c is given by, okay, 1 by beta minus alpha. Okay. So, probability of a less than x less than b is nothing but b minus a by beta minus alpha. Okay. So, let us discuss some few very simple cases. So, imagine you have a random variable, okay, x which is uniformly distributed over 0 to 10. So, let us say you want to calculate probability of 2 less than x less than 5. What is this probability? So, this is nothing, as you know from this example, your b is equal to 5, a is equal to 2. So, this probability is nothing but 5 minus 2, and beta and alpha, what is beta is 10, alpha is 0. So, 10 minus 0 is equal to 3/10. Okay. Similarly, probability of let us say 1 less than x less than 4 is nothing, will return you the same value. Okay. 2 less than x less than 5 and 1 less than x less than 4, both will return you a value of 3/10. What is probability of x greater than 6? X greater than 6 is nothing but, since you can go from 6 to 10, so x greater than 6 would be 10 minus 6 by 10 minus 0 is equal to 4/10. Okay. So, you see how you can make use of the uniform distribution to calculate each of the probabilities. Okay. Let us take one more example. Okay. So, imagine at the bus stop, okay, your buses arrive every 15 minutes. So, they arrive at 7 a.m., 7:15 a.m. and so on and so forth. Okay. So, 7:30 a.m. and so on and so forth. Okay. So, the question is, so if a person arrives at a time which is uniformly distributed between between 7 a.m. and 7:30 a.m. what is the probability of waiting less than 5 minutes. Okay. So, let us read the problem. So, the buses arrive at every 15 minutes. So, 7, 7:15, 7:30, so on and so forth. Okay. So, the person arrives at a time, okay, which is a random variable and which is uniformly distributed between 7 and 7:30, which means that person has equal chance of arriving at 7, 7:01, so on and so on, 7:01 up to 7:30. Okay. So, what is the probability of waiting less than 15 minutes? Okay, less than 5 minutes. Okay. So, since your buses arrive at 7, okay, 7:15, then 7:30. So, if he has to wait less than 5 minutes, okay, he can arrive any time between 10 to 15, okay, or 7:10 to 7:15, or any time between 7:25 to 7:30. Okay. So, what is my probability? So, this probability, okay, probability of waiting less than 5 minutes is probability of 10 less than x less than 15 plus the probability of 25 less than x less than 30. Okay. This is what? This is 5 divided by 30. Why? Because you have the entire duration is 30 minutes, and this is also 5 divided by 30. So, total is 10 by 30 equal to 1/3. Okay. Now, we can also ask the question, what is the probability of waiting more than 12 minutes? Okay. So, the bus arrives at 7, 7:15, 7:30. Okay. So, if the person has to wait more than 12 minutes, then he has to arrive greater than 7 to 7:03, right, because if he arrives at 4, then he has to wait only for 11 minutes. Okay. Since he has to wait at least, okay, of more, okay, or actually waiting at least. So, this if it is more than 12 minutes, then you will have 7 to 7:02, okay, or also 7:03 also. Okay. And similarly, he can any time between 15, right after 15 to 18. Okay. So, if he arrives just after 15, then he would have to wait for 30 minutes, which is more than 12 minutes, and latest he can arrive at 7:18. In that case, he will have to wait for exactly 12 minutes. Okay. So, my probability is nothing but probability of 0 less than x less than 3 plus probability of 15 less than x less than 18 equal to 3 by 30 plus 3 by 30 equal to 6 by 30, nothing but 1/5. Okay. So, for a uniform distribution, okay, once again I write this is 1 by beta minus alpha for alpha less than x less than beta and 0 otherwise. Okay. You can calculate the expectation of this variable is nothing but x this will return you a value of, okay, expectation will return you a value of beta minus alpha by 2. Similarly, I can calculate expectation of x square. Okay, so x cubed by 3 and x cubed is this. So, you will get a value of, sorry, I think I have made a mistake. Okay. So, wait, let me redo this. Okay. So, your expectation of x, okay, is x square. So, 1 by beta minus alpha into x square by 2 between alpha to beta equal to beta square minus alpha square by 2 into beta minus alpha, okay, is equal to alpha plus beta by 2. Okay. That makes sense. On an average, you will get a value which is average of alpha and beta. Okay. This also I will redo. So, expectation of x square is going to be 1 minus beta minus alpha into x cubed by 3, okay, is beta cubed minus alpha cubed, okay, beta square plus alpha beta plus alpha square by 3 into beta minus alpha. So, this would give you a value of beta square plus alpha beta plus alpha square into by 3. Okay. So, your variance of x then becomes alpha square by 3 minus alpha plus beta by 2 whole square. Okay. You can simplify this and see what value you get. Okay. So, that brings our discussion of uniform distribution to a close. We will now discuss one of the most important distributions, which is the normal distribution. Okay. Okay. So, what is the normal distribution? So, normal distribution is the mound shaped distributions that you see at all times. Okay. So, this is your x value, this is your probability. Okay. So, for normal distribution, okay, your f of x is given by So, you see there are two parameters here. So, your probability density function is given by f x and 1 by sigma root 2 pi e to the power minus x minus mu whole square by 2 sigma square. Okay. So, typically this peak is roughly 0.4 by sigma square. Okay. This peak is roughly 0.4 by sigma. Okay. So, we want to know what is this value mu and sigma respectively. Okay. So, for that, as again we can use the moment generating function. So, for this is equal to expectation of e to the power t x, this will be 1, I can take out this is a constant. Okay. Okay. So, phi of t then becomes, okay, I can let us say I put this mu minus y minus mu by sigma is equal to, sorry, so let me define y as x minus mu by sigma. Okay. So, phi of t becomes sigma root 2 pi. Okay. So, if I put this, then my dy is equal to dx by sigma. Okay. So, I can actually convert it. Okay. So, I have minus 2 e to the power t x e to the power minus x minus mu whole square 2 sigma square into dx, right. So, this would mean my dx is equal to sigma into dy. So, limits will not change, but if I put these values again, so dx by sigma is equal to dy. So, this sigma goes, the limits remain unchanged, power sigma y plus mu, okay, y square by 2 into dy. Okay. So, I can take into t. Okay. So, I can take this mu t term out, okay, because the integral is over y, okay, and I can write it as minus infinity to infinity e to the power, okay, minus y square minus 2 sigma, okay, plus y by 2 into dy. Right. So, we have minus y squared d minus y square by 2 minus 2 sigma. Okay. So, this you can, so minus 2 sigma is what you get. Okay. Okay. So, this is plus. Okay. So, this I can write as e to the power mu t by root 2 pi. I can write minus infinity to infinity exponential. So, within the exponential I can write it as y minus sigma t whole square by 2 plus sigma square t square by 2 into dy. Okay. So, I can take out this term again. So, I can write it as e to the power mu t plus sigma square t square by 2 by root 2 pi can be separate. So, this is exponential together into 1 by root 2 pi minus infinity to infinity e to the power minus y minus sigma t whole square by 2 dy. Okay. So, this term is nothing but the same distribution f of x with parameter of mu is equal to sigma t and sigma is equal to 1. Okay. So, this integral gives you nothing but 1. Okay. So, I can then write the entire phi of t is nothing but exponential mu t plus sigma square t square by 2. Okay. So, phi prime t then becomes simply mu plus sigma square t into exponential of the same thing. Okay. So, phi prime 0 is equal to expectation of x, which will be giving me nothing but mu. If you put t equal to 0 here, this will return you a value of 0, this will return you a value of 0. So, exponential of 0 is 1, this will return you a value of 0. So, only you get this mu. So, expectation of x is equal to mu. Phi double prime of 0. Okay. So, first let us find out phi double prime of t is equal to phi double prime of t is equal to sigma square exponential of mu t plus sigma square t square by 2. So, basically I have taken a derivative of this term, keeping this as constant, and plus into mu plus sigma square t exponential of mu t plus sigma square t square by 2. Okay. So, this will return you. So, phi double prime of 0 will give me a value of sigma square plus. So, t equal to 0 you only get a value of mu, here also you get a value of mu, and this whole thing is 1. Okay. So, you get a value of sigma square plus mu square. So, this is nothing but e of x square. Okay. So, variance of x, so this we have already obtained, is nothing but e of x square minus e x whole square is equal to sigma square plus mu square, sigma square plus mu square minus mu whole square, nothing as sigma square. Okay. So, you get variance of x is nothing but sigma square. Okay. So, for a normal distribution, the mean is equal to mu and the variance is equal to sigma square. Okay. And what you can also observe, that from this distribution, since this is symmetric about the center, so this is also the mode. Why? Because this is the maximum occurring value, and this is also the median. Because this is right, because this is a symmetric distribution, and for every point to the left there is another point to the right which is occurring at identical frequency. So, their average will always give you this particular value, which is nothing. So, this is nothing but mu. So, it means that for a normal distribution, so mean is equal to median is equal to mode. Now, for this, if I know that f of x is defined as 1 by sigma root 2 pi e to the power minus x minus mu whole square by 2 sigma square, right. So, I can define this variable z as x minus mu by sigma, then f x. Okay. So, this f x I can then find out a cumulative distribution function. So, this becomes f of z, okay, becomes, okay, 1 by root 2 pi e to the power minus z square by 2, okay, and the cumulative distribution function okay, of phi of x, okay, phi of x then becomes 1 by root 2 pi into minus infinity to infinity e to the power minus y square by 2 dy, okay, minus infinity to x, okay, minus infinity less than x less than infinity. Okay. So, this is your value. So, what is phi of x for this distribution? Okay. For any value x, phi of x is this area under the curve. Okay. This is your total probability of finding any x in any value less than x. Okay. So, we can write down for the normal distribution. Okay. So, for probability of x less than b is nothing but probability of z less than b minus mu by sigma, okay, is equal to phi of b minus mu by sigma. Okay. So, this is the value. So, these values of phi are all been computed, and you can find them from tables, existing tables, okay, in any statistics book. Okay. So, I can write down. So, if this is probability of x less than b, okay, as I drew earlier. So, for any b, this is my probability of x less than b. So, I can find out for z variable what is the corresponds to. So, this corresponds to b minus mu by sigma, and accordingly I can look this up value up. Okay. I can write probability of a less than x less than b is nothing but phi of b minus mu by sigma minus phi of a minus mu by sigma. Okay. So, one more thing, because of symmetry, okay, if this is your distribution, okay, so this is for the entire x. For phi, actually you will have mean is always equal to 0, right. So, for phi mean is always equal to 0. Okay. So, you have minus infinity to infinity. So, for any value x, right, so this area will also be equal to this area. Okay. In other words, so phi of minus x, so let us say this is value of x and this is minus x. So, this is your z axis, right. So, phi of minus x, you know this area and this area are exactly small. Okay. So, I can write phi of minus x is equal to 1 minus phi of x. Okay. So, this whole area is unity, entire integration will return you a value of unity, and this area is nothing but whole area minus this area, and this comes because of symmetry. Okay. So, accordingly, by looking up these phi values, I can find out any particular value where x has a value less or equal to 1, okay, less or equal to infinity. Okay. So, let us just take one sample example. Okay. So, if x is a normal random variable with mu is 3 and sigma square equal to 16, we want to calculate probability of x less than 11. So, how do I calculate? I just define z is equal to x minus mu by sigma. In this case, it is x minus 3 by 4. Okay. So, p of x less than 11 is nothing that probability of z less than 11 minus 3 by 4 is equal to phi of 2. Okay. So, you can find out just by looking up this value what is the value of probability of x less than by looking up the table. Okay. Let us take another example. Okay. Let us say you have gasoline used in compact cars. Generally, okay, have mileage of 35 miles per gallon with standard deviation of 4.5 miles per gallon. So, if a company wants to make a car that outperforms 95% of cars in the market, what must be the mileage? So, essentially we have been asked to ask for what value of x naught, for what value of x naught do we get probability equal to 0.95. So, what do? We define z naught as x naught minus 35 by 4.5, and find out. So, we want to find out for what value of z naught, by looking up the table, what value of z naught do we get? Probability of z naught is 0.95. Once we know that, so for example, if you look up the normal distribution tables, you will see that z naught is roughly 1.645. So, then you can use this equation to invert and find out what is the value of x naught. So, that completes our discussion of normal distribution. So, today we briefly discussed about some cases of uniform distribution, and then we came and described about normal distribution. So, for a normal distribution we derived that your expectation is equal to mu and your variance is equal to sigma square. So, you can define another normal distribution, where you define, so you rescale the axis. So, you define z equal to x minus mu by sigma, then you will get a distribution which is centered at 0. So, it will have mean of 0 and standard deviation of minus sigma. With that you can, so you can use, then you can use this particular distributions to scale, and because you have tables which have these values, you can translate any variable x into a standard normal variable z, and then look up the table to find out what exactly is the value. With that, I thank you for your attention, and we will meet again in next class.